Hello students, welcome to the class of Control System 2. I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. Today we will discuss on the linear state variable feedback control. During this video lecture, we will discuss the following topics, that is the state feedback control, full state feedback, the example of state feedback control, application of state feedback KC to the controller realization, the state feedback in Simulink, Ackermann formula, and the references. First, what is the state feedback control? So state feedback involves the use of the state vector to compute the control action for specified system dynamics. Now the feedback controller means it measures the output of a process and then it manipulates the input as we require to drive the process variable toward the desired set point. Now a controller reacts to a set point changes initiated by the operators as well as random disturbances to the process variable caused by the different external forces. Now, this state feedback control, there are two more important terms. One is controllability and the observability. So, these two properties of the state models are used to study before the designing of the controller. In our last video, we have discussed in details the controllability and observability. Now the controllability deals with the possibility of forcing the system to a particular state by application of a control input. If a system is not completely state controllable, then no input will be able to control that state. On the other hand, when the initial state can be observed from the output is determined by the observability property. So if a state is not observable, then the controller will not be able to determine its behavior from the system output, and hence it will not be able to use the state to stabilize the system. So full state feedback, it is also known as the pole placement, is the method to employ the feedback control system theory to place the closed loop poles of a plant in predetermined location in the S-plane. So if we consider the general equation, the state equation becomes x dot equal to axt plus but, whereas the yt equal to cxt plus dut. Now we can use the input u to change the dynamics, and the open loop poles are actually the eigenvalues of the system matrix A. So now we can assume the linear state feedback gain vector is k. So here in this diagram we can see that if it is u and u is given to the system, then output is produced and x is the intermediate state vector. So now we can use the linear state feedback k, which is the vector actually. So we can write the equation in the form of ut is equal to r of t minus k into xt, and during this we will assume that we know the intermediate state variable exactly. So now the equation, it becomes x dot t is equal to a of xt plus b of ut will be replaced by r of t minus k of xt, which can be written as a minus bk into xt plus b into rt. But this y equation will remain same, c into xt plus d into ut. Now the design of k should be in this way, that the closed loop system matrix ACL is equal to A minus BK, and the A should be unstable, and if we design, then ACL should be stable, or we can change any poles to the desired pole location, which is known as the pole placement technique. So this is the beauty of the state feedback control. So now let us take one example. Here x dot is given as 1 1 1 2 xt, that is the system matrix is 1 1 1 2, and B matrix is given as 1 0. So from here we can see that characteristic equations is determinant of Si minus A, which gives us a square minus 3s plus 1 is equal to 0. Now we are using the linear state feedback, which is k vector, and ut is equal to minus of k1 k2 into xt, or we can write that is equal to minus k into xt. As k is a vector and A is a 2 by 2 vector, so that's why k becomes 1 by 2 matrix. So the closed loop system matrix A, that is equal to A minus Bk. So if we compare this A minus Bk, then it becomes 1 minus K1, 1 minus K2, 1 and 2. So the overall closed loop system characteristic equation becomes a square K1 minus 3 into S plus 1 minus 2K1 plus K2. Now we can choose the values of K1 and K2, and we can put the roots of the ACL anywhere in the complex plane, and that method is known as the pole placement. So by using the state feedback matrix K, we can put eigenvalues of ACL in anywhere in the complex plane according to our requirement. Next is the application of state feedback Kc to the controller realization. So first we have considered that system matrix A and B is completely controllable. Then we can put the eigenvalues of ACL in anywhere of the j omega axis using the state feedback. Now if we consider any polynomial s to the power n plus alpha 1 s to the power n minus 1 up to alpha n, there exists a solution. If it is a seesaw, then it will be unique solution, and if it is MIMO, then there will be different number of solutions, so that the determinant of Si minus A plus Bk becomes the characteristic equation. Now if this A and B is controllable, then we can find out a state feedback for which the closed loop realization will be stable. So this is a corollary. We can prove this. So we can prove this by the solution of the state feedback vector K to put the poles whenever we require the desired position. So we will consider that A and B is completely controllable. If it is not completely controllable, then it is not possible to change the pole locations, and how we can change one pole locations to another desired pole location, that part we will discuss on our next video, the pole placement technique, and as well as to transform ABCD into the controllable canonical form. It will be much more easier. So first we will consider the A and B should be completely controllable. Then we can put the eigenvalues of A matrix to the desired pole location using the state feedback KC matrix. So KC is a vector and it will have the same order. As A is the 2 by 2 matrix, then it will be 1 by 2 matrix, and if it is a n by n matrix, then K will be 1 by n matrix. So that's why KC become written as K1, K2 up to Kn. So B into K, which gives us BC into KC, that is equal to K1, K2 up to Kn, and then the remaining terms will be 0, 1, 0 like this. So the characteristic equation now it becomes A of CL is equal to AC minus BC into KC. So after the state feedback KC, the characteristic equation is determinant of SI minus ACL or SI minus A plus BC into KC. So we can consider it into the state diagram. Here we can see that x1c, x2c, x3c, whereas x3c is the derivative of x2c. So that means x2c is equal to the x3c is obtained from the integration of x2c. Similarly, x2c is obtained from the integration of x1c like this. Now the feedbacks are minus of A1 plus K1. So now we are using one more state feedback, that is part is the K1 and the actual feedback is A1, and both are the negative. So we can consider minus A1, and then we can see from x1c the feedback is coming minus of K1. So minus A1 minus K1 are adding up, and then it will be used as the common feedback. So similarly for the next term, that is minus A2 and plus K2. So minus A2 from the x2c and minus K2 from x2c are coming, and then these two are added up, and then it will be used as the feedback. In the same manner, we can consider that x3c from x3c a minus of A3 coming and minus of K3, and summation of these two are going to this summing point. So you can write that A3 minus of A3 plus K3 can be used as the state feedback. So the feedback has been changed by using the KC vector, and the remaining term B1, B2, B3 will remain same, from which we can draw the state diagram of this general equation. So the desired characteristic equation becomes s to the power n plus alpha s to the power n minus 1 up to s to a alpha n. So if now we equate the coefficient power of the s, then we can find out that k1 equal to alpha 1 minus a1 up to an. So alpha n minus an, and get the desired characteristic polynomial. So now we can solve this equation and this solution in the controller canonical form, and we can also transform back to the original realization. So the desired characteristic equation is determinant of Si minus Ac plus Bc into Kc, or we can write determinant of T into determinant of Si minus Ac plus Bc into determinant of T inverse. Now this T matrix is the modal matrix. Now, or we can write the determinant of Si minus A plus B Kc into T to the power minus 1. So from this we can use the state feedback Kc into T to the power minus 1, so that x of s is equal to determinant of Si minus A plus Bk. Or this k is the state feedback, which is equal to Kc into T to the power minus 1, whereas this Kc into T to the power minus 1 is actually alpha 1 minus A1, alpha 1 minus A2 up to alpha n minus An whole into T to the power minus 1. So using this controller canonical form, we can directly find out, or we can transform back to the original realization, whichever we need it. Next is the state feedback in the Simulink. So in the Simulink, we can also write the state feedback matrix, and the original equation x dot is equal to ax plus bu, which has been converted into x dot is equal to a into a hat minus bk plus c into u. So here this one is the Simulink diagram. So x after x can be obtained from the integration of x dot, and 1 by s represents the integration term, and b into k has been coming here. So x dot is equal to kx plus b into u into k, and r is given here, and another feedback k is attached to this system. And here also, if we consider the output, then one forward path is there, that is also represented by the k over here. Next is the Ackermann's formula for the single input, single output system. So if we consider the plant system has been represented by x dot is equal to ax plus bu and y is equal to cx, then the required state feedback is minus k into xt plus r of t, and the desired pole locations are the eigenvalues, which are represented by lambda 1, lambda 2 up to lambda n. So using this Ackermann's formula, we can find out the state feedback gain matrix. So our required characteristic polynomial becomes s minus of lambda 1. So we can put this and we can rewrite this equation s to the power n plus acn s to the power n minus 1 plus ac1. Now, as per the matrix polynomial alpha c of a, that is equal to, this will be replaced by the system matrix A. So s to the power n becomes a to the power n plus alpha cn into a to the power n minus 1 up to alpha c1 into identity matrix. So if we can put this equation, then we can write the state feedback gain matrix become k equal to 0, 0, 0 up to 1, b, ab, square b up to a to the power n minus b inverse into alpha c into a. So using this Ackermann formula also we can find out the state feedback gain matrix. These are the references, and I hope after this video lecture you have a clear idea about today's topic. Thank you.